Okay, good afternoon, everybody. I'm David, I'm from Team November, and I've been really pleased to present Survey Swarm to you. The client for our project was ARM. So who here has heard of swarm robotics before? Oh, well done, Alan. Have a Kit Kat. So we quickly found there were two components to Survey Swarm. We needed to measure out an area, map out its features, with many, many robots that comprised the swarm. Applications of this include mass surveillance across many regions, say in disaster relief or in battlefield zones. It is faster than one large, expensive robot, and has also been used to search for resources. Related work includes, in 1980s, subsumption architecture developed at MIT, the first of its kind. There's other algorithms, such as distributed algorithms and directed diffusion. Most recently, in 2014, there's an algorithm called Coleus, which is very similar to our project. We also identified three key features with Survey Swarm. We needed to measure out an area or board, which we decided to be black or white regular tiles, using a centralized server so it would be quick and would be a proof of concept. We were supplied robots called the Pololu 3Pi robots and the ARM embed from our client. The project had three key features in mind. It had to be cheap, reliable, and adaptable. This was so that we could have any number of robots possible to map out any possible flaw with just using reflectance sensors. On the other screen here is our front end. It allows the user to specify the size of the grid, the tile, and the number of robots. Interactive updates allow the user to monitor the progress as it's been scanning. The server is a backend which processes the robot position and the server for the web app. It calculates the next position for the robot and routes it. It also hosts a web app on a node server. We use frequency analysis to determine whether a tile is black or white, which is then displayed in the front end. The router is just a Wi-Fi hotspot for the server. All the robots can connect to the router using TCP and send data via JSON objects. The server then, in turn, just sends an angle and a distance for the robot to turn. The robots connected to the router and they find data samples. We know their position using time-based odometry and various sensor readings. So the two key components of a robot are straight motion and rotation, as you can see in the video. There's a trade-off between having the robots go slower and the robots go faster, as you can see in the diagram here. Thus, we had to find a balance between the two. It was hard to get the robot to move where we wanted to go because of the following reasons. We even had to put weights on the robots to ensure they remained balanced. However, it was really easy to find a reference point using line following. We decided the reference point would be a corner. We solved the problem of rotation and straight movement using these four techniques. We then found that the robots needed frequent recalibration because after two moves of the robot, the error became so large its position was no longer accurate. We needed to recalibrate its position as well as its intensity. We thus developed the following routing algorithm. We would find a corner, and then we would move to a square, and then whilst mapping out all of the intensities, before we went back and found the next corner. This is illustrated in this diagram. By constraining the magnitude of the motion of the robot, this enabled us to also divide the board into four quadrants. This enables, at any one given time, four robots to map out the quadrant, and so on, as shown in the diagram. This also means that the robots will not theoretically collide with each other. When we tested it, we aimed to achieve over 75% accuracy. We used unit and regression testing on GitHub and Travis CLI. So, in conclusion, we have implemented the following key features. We have an accurate positioning system, enabling the robots to quickly recover if there's a problem. We have a reliable routing algorithm, enabling the robots to go throughout the board, and a responsive web app. If we had more time, we would encourage the clients to take these further steps. We'd like to explore it with more than 4 robots. We'd like to explore also irregular floor sizes other than the square we have. We're also interested in using continuous rather than discrete values. This means that instead of having just black and just white and having all the tiles in a regular size, we would have, say, more colors. And this could be achieved by just changing the sensors and using other more fancy computer vision techniques. So before I finish, I'd like to thank the following people for all their advice and for their assistance. Without them, we could not have completed the project on time, and I'd like to thank you all very much for listening. Thank you.